Good morning. In today's session, we will learn about the design of IAR filters using impulse invariance technique. Okay. Now, impulse invariance is a technique for designing discrete time infinite impulse response, that is IR filters, from continuous time filters in which impulse response of continuous time system is sampled to produce impulse response of the discrete time system. So here the main concept that we do is sampling, that is the continuous time filters. Here the impulse response of continuous time system is sampled in order to produce the impulse response of the discrete time system. That method of designing IR filter is called impulse invariance technique. Then the same thing is repeated here also. A technique, the impulse invariance technique is mainly used for digitizing an analog filter. That means to convert analog filter into a digital filter is called impulse invariance transformation. The main objective of this method is to develop IR filter transfer function whose impulse response is the sampled version of the impulse response of the analog filter. So here the impulse response of analog filter, as I already said, it is sampled to get the impulse response of the corresponding digital filter. Now the main idea behind this technique is to preserve the frequency response characteristics of the analog filter. In the consequence of the result, the frequency response of digital filter is an aliased version of the frequency response of the corresponding analog filter. So here main concept here what we do is sampling. The impulse response of analog filter is sampled to get the impulse response of the corresponding digital filter. Now to develop the necessary design formula for impulse invariance method, we are first considering a stable analog transfer function, and it is represented as h of a s. Now its impulse response is represented as mod h of a t. Okay, it is given by the inverse Laplace transform of h of a s, that is the analog transfer function h of a h a of s. We are taking the inverse Laplace transform of the analog transfer function to get its corresponding impulse response hat. Okay, this is how it is represented. Laplace transform of analog transfer function ha of s is taken to get the impulse response ha of t, equation 1. Now in this method we require the unit sample response, that is represented as h of n of the desired casual digital transfer function hz. Hz is the transfer function in terms of digital filter. Now it is given by the sampled version of ha of t sampled at uniform time interval t seconds. So then how it is represented, that is h of n. This words is just represented in the form of mathematical expression. Okay, that is h of n. What is h of n? Unit sample response of digital filter is equal to this ha of nt, that is it is sampling is represented as n. It is n times its sample. T is a sampling period where n is an integer ranging from 0, 1, 2, etc. Okay. Now in order to investigate the mapping of points between Z plane and S plane, what is Z plane? Digital filter, S plane analog filter. So in order to understand this mapping between this digital and analog filter systems, we are first considering the Z transform is related to Laplace transform of h of a t, as that is what is h of is a transfer function of digital system is given by z, that is the z transform of this one ha of nt. What is ha of nt? We have already seen. Okay, we are taking the z transform of this ha of nt, okay, to get the transfer function of the digital filter h of z. Now some steps are skipped here, and this will reduce us to this particular expression where h of z is given by this one, and h of z at z equal to e raised to st is given by this expression. So I think you can write this step first, then this step, and then write where h of z equal to this one. Okay, now this is again represented in terms at we are giving a particular value for z in terms of exponential form, that is z equal to e raised to st. Okay, so this z is replaced by e raised to st, t sampling period. Okay, so where s is given, it is given as sigma plus j omega. Now we are examining the transform z e raised to st of equation 4, which is again written in another form as z equal to e raised to st, where we know s equal to z plus j omega, and so z is again written in this form. Okay, z equal to e raised to st, e raised to st. This is again written like this. Then omega is represented by e raised to omega t, where omega equal to this omega t, t sampling period. Omega, this omega representation represents angular frequency, and this omega represents the frequency in digital domain. Okay, this both this omega and omega represents frequency, but this symbol represents the frequency in analog system, whereas this one represents frequency in digital system. So now we'll see the development of transformation, or how it is developed. So in many textbooks I have referred, and it is a very lengthy procedure, that is they have skipped many steps in between. So we are actually studying these equations as such. If we include all the proof in between, it will be very lengthy. At the same time, you won't be able to finish your exams. Okay, so I have taken the most shortest one that is possible. Okay, in some textbooks it is elaborated very much, so including all the proofs, that is how this step is obtained and all it is given. So if you write that, it will be very difficult for you to present in the exam. So if you want to know how this is obtained, you can, I think you can refer some those books that are described in detail. Okay, from exam point of view, I think this is enough, because this is the shortest one that you can find. Okay, so try to learn. Now development of transformation. Now to explore the effect of impulse invariance design method on the characteristics of resultant filter, we are considering a system function of analog filter in partial fraction form, and we are considering this h of a s, that is a transfer function in analog system, represented by this particular symbol, where this one, some set of ak are actually the coefficients in partial fraction expansion, and pk are actually poles of the analog filter. All these are explained in detail. Now the impulse response ha of t corresponding to equation 7, this particular equation is represented here like this. Now u of nt is the continuous time step function. Now next we are sampling this ha of t we obtained, that is equation 8. Now we are going to sample this ha of t periodically at a time period t, that is we are replacing t as n of t. So what will happen, h of a in place of t we are writing n of nt. This one is written as such, ak is also written as such, pk of t is in place of t you are just introducing n of t because we are sampling. Then u of a t, and in place of t you are writing n of t. So this equation is same as this, but the only thing is that in place of t you are writing n of t. Why? We are sampling ha of t. Okay, then now the system function hz. Okay, the digital filter is the z transform of this sequence and is defined by this equation. Okay, we are taking the summation here from n equal to 0 to infinity and is numbered as equation 10. So the equation 10 will then become sigma n from 0 to infinity a of k e raised to pk of nt is raised to minus n. Then again we are taking this a of k is assumed to be 1, and the z raised to minus 1 is splitted up as z raised to minus 1 whole raised to n. We are just rewriting z raised to minus n as this. Then again it is written in another way, a of k then in this form 1 by this term. Now there is a condition, e raised to p of kt should be less than 1, and that condition will be satisfied only if the coefficient p of k is less than 0. So this means that this transfer function h of a s is a stable transfer function. Now from the last equation we observe that the digital filter will have poles at these values. So here we are finding out the region where the poles of digital filter can be seen. Now by comparing expressions 13 and 17, we see that impulse invariance transformation is accomplished by the mapping. That is, we are just mapping from S plane to Z plane. This is the S plane, Z plane. This is how the mapping look like. Similarly, from S plane to Z plane. Now there is a slight procedure for designing an IR filter using impulse invariance technique. That is, if this is very lengthy, you can either follow this step also. We are just briefing what it is earlier said. The transfer function in S domain, you will be given the transfer function is in S domain. Now we have to first find impulse response h of t. Now the second step, we are sampling h of t to get h of n. Finally we find h of z, that is in the z plane or the digital system. So you are given an S transfer function in the S plane, that is in the analog form, and finally you are converting it to Z plane, that is to digital form. Now suppose that consider you are given the system with the poles like this, h of s and h of t. Now we are first of all substituting t, that is we are sampling h of t. How? By putting t is equal to n of t in equation 16. So you will get this expression, and h of z or the transfer function in z plane also. This is how the mapping is done. Now this will be demonstrated with the help of an example. The same thing. Here they are given in the question, they will be given a transfer function in the S plane, that is in the analog system. See, they are given. Okay, now first we are splitting in terms of partial fractions. You know how to split this one into partial fractions. You are putting a constant k1 and k2. Okay, then what we do? We are calculating the value of k1 and k2, just the procedure of solving a partial fraction. So you got the value of k1 and k2 as 1 and minus 1. So how equation 1 will look like, provided k1 is 1 and k2 is minus 1, it will look like this. So you got the transfer function in the S plane or in the analog system. Now you have to convert it into digital system. So the first step, the next steps to do is we have to calculate h of t. How will you calculate h of t? That is, this is of this form, that is 1 by s plus 1 is of the form 1 by s plus a, that is actually equal to e raised to ax. You have studied in Laplace transform, right? 1 plus s. So in place of a, here it is 1. So 1 by s plus 1 will be e raised to x and so on. So like that you have to find uh, okay, e raised to ax is equal to 1 by s minus a. Is so it will be, a will be uh, minus 1, so that is minus t. So h of t will be e raised to minus t minus, here there is a 2, and that is why we have written e raised to minus 2t. Then we have to calculate h of n. How? By sampling h of t, that is in place of small t we have to put n of t. See, it is also written. Now we are evaluating z. So this first term in terms of z transform, it will be z by z minus e raised to minus t, and here there is a 2, so z by z minus e raised to minus 2t. This is how it is obtained. So this is no need of studying this problem, it is just for your information. Okay, and these steps I think you can study. Now the impulse response, the definition, it is only from here you have to study the definition, then how to design or how to convert, the how to map from S system to Z system, and the steps for development. These 4 slides you'll have to study. So if you want to know more about how this step come from like this and all, you can, I think you can refer some reference books. In that it will be described in detail, so you will know how this is converted to this and this is converted to this and like that. But don't try to present it for exam, because it will take a lot of time and you won't be able to reach at the final answer, so you will lose mark. Okay, so go for the shortest description. Okay, then only you will be able to complete in time. So if you study this, this 4 slides is enough to write for the exams. Okay, for reference you can refer books also, but for our exam point of view, I think this one is better. Okay, thank you.